All right, so I asked you a few questions related to watching that video. Nope, not that. Here's what I'm looking to click on. Ooh, all sorts of stuff we're going to be doing in the near future. I'm sure you're excited. So, for each frame of that same race, I asked you a few questions. This was not one of them. But thinking about these, if someone say, oh, well, he ran this 100-meter sprint by running running it in 9.58 seconds. If someone asked, how fast was he running? What's kind of the problem with that question? What might be challenging about answering that the way that you want to answer it? Yeah. Yeah, he's probably not running at a constant rate. How can you tell by watching this or by having ever run in your life? Well, think about, like, at the beginning, they're all hunched down, standing perfectly still. Whatever he might have gotten to as a fastest speed, I don't know. He's a good runner. I'm sure he tried to get to his fastest possible speed as soon as possible. Or if he had a fastest possible speed, he'd probably try to run faster than that. But if we're talking about somebody running over a period of even a short amount of time, 9.58 seconds, there's bound to be slower parts of that and faster parts of that, right? Probably not, right at the start, he can't be instantaneously from 0 to some speed, whatever that might be. Which, whatever I could say about that, if I said, oh, 100 meters in 9.58 seconds, if you're running at a constant speed for that length of time, or if some car was driving at a constant speed, which might be more reasonable for a car to maintain an exactly constant speed for, not when it started, but as it was driving for some 9.58 second period for its speed to remain essentially constant, how would you figure out what that speed is if you have this sort of information? If it was going to be a constant speed, how would you compute that constant speed? Right, that sounds good. So the distance traveled divided by the time it took to travel that distance. So if we were talking about one constant speed, then we could take total distance divided by total time elapsed, distance traveled divided by time it took to go that far, and that would be the speed. Now, in this sense, if I did the same thing for him, it wouldn't be what speed he is going the whole time. What would that actually be relative to somebody that's traveling at a variety of speeds? What can we call that instead? Yeah, that'd be called an average speed. His average speed, and it's not by averaging a bunch of different speeds, just an average speed is the speed that equates to the constant rate it would take to accomplish the same distance traveled in this case, the same whatever it is that's happening due to this rate. If you have an average rate, that average rate measures or it tells you what is the constant rate that it would take to accomplish this same thing, which in this case, what's the constant speed he would have to run if you were able to run at one constant speed for 9.58 seconds to go 100 meters. That's the constant speed it would take. Now, was he going a constant speed? We said no. So let me show you a graph of his distance. This is modeled based on data points. Track is very high-tech these days. They can tell you where you are precisely at any point in time during the race. Now, usually it's only a few data points. It's not a whole bunch. But if you want to look at it after the fact, video can also provide you with those because of all the high-tech video sorts of things we can do. I'll get back to that in a minute, but that's for later. Here we go. I showed you this graph over the weekend as well, and you have a version of this now available to you in a GC file. We're going to play around with this a little bit today and do an activity in a bit, but this is a graph of that function up there, which that function was designed to model his position on the track relative to the starting line measured in meters, where the independent variable is time elapsed since the starting gun went off. And you can see even world-class runners, it takes him a little while to get going, right? After 1 second, he's not gone too far. At the end though, if you look at this, I can see the beginning is something that looks like going slow and then going faster. Visually speaking, what is it that I'm seeing that you're probably also seeing that means like going slow and then going faster? Yeah, so, okay, so physically speaking, it'd be acceleration. Um, Visually about this graph, just looking at the shape of it. Shapes don't tell you everything unless you know, what exactly is being demonstrated in the graph. You can interpret some things from it, but something about the shape of this tells me speeding up. Okay, it's curved and it's getting steeper. So yeah, it's kind of flat at the beginning and then steeper later. So why does steeper correlate to faster? So for instance, if I'm looking at a section up here, or this whole section in the center looks kind of the same from a distance, seeing it all without zooming in, versus this beginning part, from probably experience and having looked at things like this before, that means, oh, slower and then faster. This isn't a graph of his speed. Isn't it speed near 0 and then a speed near 80? This is a graph of his distance. So if I want to see speed or his rate of change of position down the track with respect to time, if we want to be very mathematical and weird sounding about it. But if I want to talk about his change in position relative to his change in time, that's his speed. Thinking about the, angle, not in degrees, but just relatively speaking, how much up to how much over, that's precisely that ratio dy over dx, or how much change there is vertically relative to horizontally. Thinking about things that we did last time when we did have constant rates of change, forever within the domains we were talking about, like the flag lowering at a constant rate, like gas costs increasing at a constant rate of $2 per gallon. This section looks kind of like that, because every time I go over any amount, the amount up that I go seems to be about the same, not the same as x, but the same as looking at a different section. Or if I looked at a small section, go over one little block, I go up a block. Or go over 2 blocks and I go up 2 blocks. It seems to be about the same rate of vertical to horizontal throughout this right part, but this less steep, thinking about the beginning, this less steep part, which kind of means slower, thinking about why, if I were to go the same amount of time forward, think about one block graph-wise, grid paper, one grid mark forward, I'd go less up at the beginning, so less distance traveled in one block of time here than the distance traveled in one block of time there. To not put any numbers to it, we have the ability to do that. We have a function rule up above. So the ratio of up to over, or over to across, I guess is what I'm talking about, vertical to horizontal change, when we're looking at this Cartesian xy plane graph, that ratio there is his speed. And so his speed, we know, is different in various parts, but how can we even talk about that ratio of up to over when it's not really a straight line? That's kind of our question for this week. Can we deal with that? Can I deal with talking about rates when I don't have exactly a straight line? I have a 5th degree polynomial here. So when I only look at this section of it, the idea is that, well, even from a distance, a lot of this looks like a linear function. A lot of it looks like it's increasing with the same ratio of change in y to change in x, or dy's over dx's. It looks like it, just visually. We have a formula here. We can compute those, and that's what we're going to be spending today's time on, looking at computations in this, but I'm going to have you play along with me. So if you open up your Canvas page, let's see, on Canvas, if you don't have a computer, please look on with someone else, but on Canvas, under Module 2, which is where our stuff for this week's going to be, you'll see a file that's called Usain Rate Work GC file for Monday. If you open that up, you'll get something that looks mostly like what I just had. It just doesn't have those little black dots in it. You can see there's little black dots around 3, and I asked you about the little black dots in your questions. So the questions that I asked over the weekend were, in addition to is he traveling at a constant speed, how do you know? Or how do you know he's not traveling at a constant speed, I think it was. What if I just look at a little tiny amount of time right around 3 seconds into the race? If I were to look at a little tiny bit of time 3 seconds into the race, and let me show you how you could do that. Now we're going to, if I want to zoom in on a particular portion of this graph instead of just generally zoom in and zoom out, a technique you can use is like a shift click. So if I have this section here I want to zoom in on, I'm going to hold my mouse key down, let's see, hold the shift key down and then put my cursor where I want and kind of drag a rectangle around it. So just a one finger drag something around this. If I want to zoom in on that part, then I let go and it zoomed in. Now, yours doesn't have all this stuff in it right now. So yours, if you did that right around 3, there weren't little black dots, and I think you'll see that purple arrow. But what I'd like you to do, we're going to work together on this, is to make something where, first of all, you only see part of the graph, 0 to 9.58 seconds, by graphing this function up above. So f of t is defined. If you want to actually see this whole graph, which I think it might already be on there. I don't know if it was on there or not, but if you want to see that graph, there's a question mark. Under task 1, there's a question mark. It's just a blank command line. If you put your cursor there, thinking about GC and how you remember how it works, if you can put your cursor there, you can make a graph of whatever XY relationship you tell it to graph. And if you do it efficiently, you can do that in just a few characters typing, as opposed to typing all of this. Because I want it to show this relationship with X as the independent variable and Y as the dependent variable. So to get it to show a graph of that, what do you need to type as a command line just generally to show a graph? Y equals something. And then if I want to show the graph of that relationship, y equals f of x. Right. So if you type y equals f of x, it won't look like what I had. It'll look a lot bigger than that. Let's see. Reset. And your graph might also look like this. Like, oh, well, I don't want that. I don't want this, like, I only need x to go from 0 to 10-ish or so. In fact, I only want to show 0 through 9.58 seconds. And the vertical axis, I know, is the distance he's run. So I need that to go up to like 100 or so, because he's running 100 meters, maybe a little bit past that. If you restrict your domain, you can graph part of this graph, so it stops at 9.58, so you can just see the part that corresponds to while the race was running. If you remember the Unser Montoya thing, the race ends when the winner wins. I mean, everybody else wants to know what their time is too, but when the race is over, that's 9.58 seconds. With regard to Usain Bolt, at least, he doesn't care when second place finished. I don't know, maybe he does, as long as it's after him. But if you type in your domain restriction, you can get just part of the graph. Now, if you have a graph that looks kind of like this, like that's not what I want, you can arrange, you can zoom in, zoom out, but play around with your graph so you can get it back to like what mine looked like when I just opened it. You can see the whole thing. So whether that's go to the graph area and set a range and then play around with it from there, like x needs to go from 0 to 10 or so, y needs to go from 0 to 100 or so. I'll put 110 so there's a little space. But that way you can see what you want, and then you can center it in later. So you can drag the axes around. There's not really going to be a way to, it's going to start looking shorter and shorter if you try to stretch it out wider. But what yours doesn't have in it right now, if you have the graph, is these dots down here that I was showing you. We're going to use those for something in particular. So look at, well, we're going to do some computations today, first of all. But there's 2 more tasks down below here, which have to do with, here, let me move this down a little bit. I want to be able to change this value of C and a value of dx and make stuff happen. So what's going on here? If you can see this little, I have little black dots there. You do not yet, because your next task is plot the point for the current value of time, x equals c, and for a value of time dx later. Now yours will say c equals 3, and you can change that to other numbers. Let's just do 3 for an example. So if yours doesn't say 3 in this c equals line, that's just defining a parameter value. You should have this dx equals slider, and you can play around with that if you want. But what you don't have is a couple of dots, and what those dots are is the stuff that's going on at 3 right now. So if I want to plot points for the current value of time, so let's say current value is c equals 3. I'm going to zoom in here and show you what you want to have happen. Now the arrow is going to be there, but shift click is what I'm doing to get this little box, and then zoom in like before. What you should have this arrow showing there already, I believe. But what you don't have is a dot at the beginning and the end to kind of help magnify that, to make it clear that we're looking at that specific interval. So underneath this task 2, you should see 2 of those vertical brackets, and they're empty, full of question marks or something. If you click on them, you can fill them in, and what I'd like you to do is fill in not numbers, but expressions involving c. C was defined earlier. C is 3 right now, and we can change it later. It's a parameter. But so that this point starts at x equals c, and it's on that curve that we have graphed, and that this point is dx later, and dx is also a parameter. It's defined by the slider, so it has to be able to move, but you don't have to type anything fancy. Just dx is how much later, horizontally speaking, so time-wise, later in time, the second point is than the first. And so when you go to type into those 2 brackets to make your 2 dots, it shouldn't matter what value dx has. Just use the symbol dx and use the symbol c and some other stuff to make those 2 dots appear. We'll worry about the m in a second. Yours doesn't have a value for m calculated, and mine does. So see if you can get those 2 dots to show up, one at point c and one at a value of time that's dx later. Dx farther to the right, but also on that f of x curve, the function that relates Usain Bolt's time that he's been running to his distance down the track. So if you get those in, you should be able to go back up to your dx slider and make it do this with your dot moving along with the point of the arrow and the other at the base of the arrow. So again, the beginning of the arrow is at the current value of x, x equals c, and c is just defined above. And if you change that parameter, your arrow should change along with it. But let's stick with 3 for right now. So the second point takes place at a time that's dx later. So dx can take on a variety of values, but I want that second point to be dx seconds later in time. So think about what expression you could write that would make sure that the value is dx seconds to the right of the first one and on the curve also. Which, I say on the curve, but look at this graph from this level of zooming. Doesn't look too curved. So for instance, the first point here, if the x value is the current value c, I can have c, f of c for that point, right? What would I need for the x coordinate, the first part of the correspondence point at the second dot? C plus dx. So how would I figure out how to express the dependent value at that same point? Yeah, f of that. So f of c plus dx. Now those are on a curve, but from this view, it looks like they're on a line, right? Task 3 is to have this m computation come up here. So if these are the 2 points, and they look basically like they're on this straight segment, or within this region on the graph, if I zoom in this far to this small amount of time between 2.7 and 3.4 seconds, looks pretty much like a straight line. Like looking at the shape of it is what you're used to seeing. Like, oh, that's going up, that's going at the same speed as compared to when you're zoomed out and you can see that it was slower at first and faster later, just from general being used to looking at things like this. But really what that is, that's that ratio of, visually speaking, distance to time passed. The rate of change of the distance with respect to time, or as speed, is given by analyzing how large that ratio is. So if I want to compute that speed, m, or compute the, visually speaking, I could call it steepness, but what this is how fast he's going. The ratio of vertical change to horizontal change, or distance traveled during a certain amount of time that elapsed. When I'm talking about 100 meters in 9.58 seconds, we know he wasn't really going the same speed the whole time, but over a little tiny, like this is half a second, no, 5/100ths of a second, 3 to 3.05 is what that looks like about now. Over that amount of time, he probably isn't capable of changing his speed too much. That's an awfully fast, awfully short period of time to either accelerate or decelerate during for a person. So if I wanted to compute what his speed is during this interval here, we talked about this with 100 meters before, but over this interval, well, generally speaking, what can I do, not just specifically with 3 and 3.05 or 6 or whatever it's at, how could I express that rate of change in general with these c's and dx's? Yeah.
F of c plus dx minus f of c over c plus dx.
All right, so yeah, y final minus y initial over x final minus x initial, kind of general slope computation that you did since algebra or pre-algebra. Notice that if you do that, you could also simplify that denominator. C plus dx minus c is just going to be dx. Can you do the same with the numerator? Is the position at time c plus dx minus the position at time c just equal to the position at time dx? I don't even know what time dx is. That'd be like 0.05 or whatever seconds into the race. So yeah, these are function notations with input. It's not multiplication, so I can't actually do that numerator subtraction. The denominator, though, is just subtracting quantities c plus dx minus c. The c's can cancel out, leaving us with just dx. So you can simplify the denominator of that expression as you want, and if you do that, and write this m as your task 3, if you go back up to the top, you should have a number appear for m. This was set to show the value of m. We just didn't have the computation written in for it yet. So what this means is I can look at his speed during this interval. Now it's changing, so I know if I move this slider back and forth, for these different values of dx, I get different speeds, but they're pretty similar. Right? So if I look at what happens between time 3 and time when dx is 0.1 here, time 3 and time 3.1, it shows a speed of, what would be the units on this? It says 10.828 meters per second, right? Because our f of values, our dependent variable values, were his distance measured in meters, and our independent values were times in seconds. So this would be a ratio of meters to seconds. So meters per second, 10.828. When I have a larger dx value, if I make it smaller, maybe if dx is 0.054, I've got 10.805, which isn't too much different. 10.805 to 10.828. It's a different number though, so that lets us know, despite what it looks like, this isn't exactly a straight line. Because if this were precisely a straight line, no matter how large my dx was, I would have the same rate of change, that same ratio for m, the same multiplier for m to get from dx to dy. Now, notice if I have dx all the way down to 0, it doesn't give me a value. So what that's trying to compute, so you think about it, if dx were 0, that'd be trying to compute his speed between time 3 and time 3. Well, if no time has passed, then you can't have changed anywhere. So there's no rate of change if you don't have any change. So you can think about, oh, how fast am I going now? But like, I could be walking like, oh, how fast am I going now? But if like you freeze frame at any point in time, how fast am I going now? Well, I'm by freezing. Like, imagine time was able to freeze too. I can't perform that ability. But if time freezes, then there is no change in anything. Everything's frozen. So in order to be talking about a rate of change, you have to have small amounts of change. So I can imagine, and I just have this set to be like divide up 0.1 into 100 parts. So the smallest amount of change, if I fuss around with this, I might be able to click on it appropriately to get dx as 0.0001. I could set this so that I could have 0.000001, but I have to have some increment of time go by. Otherwise, there's no motion happening. So there'd be no way to compare distance traveled and time passed if there's no time that's passed. So looking at this smallest, when c is 3, the smallest dx that I have this program to show, 0.001, 1/1000th of a second, during that thousandth of a second, he moved some small amount. Now you can see your dots would be right on top of one another, but I can zoom in closer, shift click, say, well, this is 1/1000th of a second, spread out far. That's the shortest I can make this arrow, and just because of how I programmed the slider here. But he did travel some distance during that time. It's just not a heck of a lot. In 1/1000th of a second, he traveled some number of meters. We don't need to calculate out what it is, but I can see from this, I could actually calculate it using that. In that 1/1000th of a second, I bet his speed didn't change very much. So this is a good, I can pretend I'm using this constant speed for a full 1,000th of a second. And so over this 1,000th of a second, it says m is 10.7778. Okay, that's still pretty close to that 10.828 we had with a 1/10 of a second. It's off by, what, half of a 1/10, let's see, a 20th of a meter, whatever that would be. Which is, you know, that's a distance that you could see with your eyes. It's not microscopically small distance traveled. But in this 1,000th of a second, he traveled 10 times as far measured in meters, or 10.778 times as far in meters, if we assume that this is a constant rate. So over this small interval, I can think of this rate as being constant because there's hardly any time for him to change speeds. This is 1,000th of a second. I can make it to be a 1,000,000th of a second, and maybe it'd be slightly more accurate. But you can see if I change from 1,000th of a second to 4,000ths of a second, this changed from 10.778 to 10.779 something. So it's a very small amount of change for this value of m. And again, the idea is this m is what relates dx and dy if I'm assuming constant rate of change. And I want to use constant rate of change in these slightly not constant all the time situations. In order to do so, what we're going to do is limit ourselves to looking at small intervals. If I look at a small interval and I use one constant rate for a small period of time, and then readjust later because, well, it does look like maybe it's getting a little steeper later or a little flatter later, visually speaking, just visually speaking, these computations, you can see that that M changes when you're at different positions of the graph. But if you only use them for a little bit, you're not going to be off by very much. So we can recreate his whole run by knowing what his speeds were at various moments of time. Now, I don't really want to say at various instants, just because an instant seems like it's one spot. I have to have a little tiny interval of time go by in order to have some amount of change or be able to measure the distance traveled. But as long as I just use small intervals of time to do these computations, I can get these approximate values for a constant rate. And I'll say, well, over this interval, his rate is approximately constant because, well, the number doesn't change too much for this rate. So I can say 10.77 something and 10.77 something else. It's about the same speed in meters per second, 10.778 or 10.777 meters per second. They're about the same. So I've got an approximately constant rate during this smallish amount of time that's passed. So why this is useful, again, because not everything changes at a constant rate all the time, but we can use our tools of constant rate of change to measure a change in y based on a change in x, whatever the x and y might relate, and then also to get new y values from old ones by using a constant rate for a little interval. So let me jump back to some terminology and whatnot, and then we're going to do some more with this graph in a second. But let me just take a short break from this, and not that one. I don't know why that keeps opening. All right, so move this over so I don't write super huge the first time I try to write anything. All right, so looking back at this then, if I said, what would it mean that at 1 second after the start, he was running at 6.148 meters per second? Well, we've used constant rates to describe lots of things. First thing you might think of is like, oh, so after 1 second, he would have run another 6.148 meters. Do you think that's true if he's Usain Bolt? No, he'd probably speed up, right? Even during a second, he'd probably be faster, appreciably faster by the end of that whole second. So instead of using the simple 1 second at a time interpretation, remember the meaning of this constant rate of change. Over any number of seconds that this applies to, the distance traveled would be 6.148 times as much, and we measure that distance in meters. Now, since we're talking about Usain Bolt here, not somebody that's running at this one constant speed forever, he's probably going to speed up. This is only 1 second into the race. And this picture here, I'm pointing at my screen, that's not helpful. This picture here is exactly at 1 second into the race. So there he is. He's a certain distance from the starting line, not too far. We can still see the starting blocks. Over a small amount of time, maybe like the next 0.05 seconds, he'd probably travel at 0.05 times 6.148, that number of meters. Because over maybe 0.05, 1/20th, is that 1/20th? Yeah, 1/20th, 1/25th, whatever that is. 0.05 of a second, 0.05 times that, because he probably can't speed up or slow down too much in that tiny amount of time, that would probably be a good estimation of how far he traveled. So instead of talking about any amount of time passing, if we talk about a small amount of time passing, we can use this rate even though we know he's going to be changing speeds later. But if we only use this speed for a little bit, we can talk about how far he's traveling. Now, if I look at it like this, a freeze frame picture, how fast is he moving in that picture? He's not. It's not a Harry Potter picture. He's just frozen in time. So if I want to talk about at one value of time, how fast is anything changing? At one value of time, nothing is changing. At one value of time, there's one position on the track, and that's it. So there's no speed that we can measure. But here's what I was saying earlier about talking about a small moment of time. So if I think about this, just refer to a moment. So I'm going to use the word moment, and your book will use the word moment to refer to kind of emphasize that it's not like if you say just a moment, you don't mean like instantaneously something happens. There's like a small pause, and then something happens. So if I say during a moment when we're 1 second into the race, what we mean by that is think about the time 1 second and a small interval of time around that, whether it's on both sides of it, just later than that, just earlier than that, but just a small increment of time that includes somehow or another this time of 1 second. If I want to measure speed, I have to have an interval. I can't have just one value. Now I can apply that speed and say he was going whatever speed I come up with at x equals 1 or at a moment when x equals 1. And so we will apply one value of speed to a particular time, but in order to compute it, we have to have an interval. So we're going to talk about a small moment of time around x equals 1 or at x equals 1. Using that word moment, we're indicating that there is actually some small interval or small amount of time that's elapsed. So if you see this question, like, oh, well, I could figure that out. If I look at where he is at time 1 and time 1.0001, I could do a speed calculation based on the function that we had on the GC file. We could come up with a speed for that. Or maybe it's 0.999 to 0.1001 or 1.001. I could look on either side and do, it doesn't matter precisely what interval we're talking about, but just some small interval. And there is a one-sentence section in your book that's titled in chapter 4, How Small is Small Enough? Small enough depends on your situation. If we're talking about something traveling near the speed of light, 0.001 seconds is probably not small enough. If we're talking about somebody walking down the street, 0.001 seconds is probably plenty small enough. So it depends on the situation, what we're talking about, how small is small enough. But if you have a relationship, an XY relationship that you're trying to measure constant rates of change from, small enough is small enough so that it looks like what we saw there. It looks visually like you've got a constant rate. Or if you do computations like we had with that m, if the m isn't changing very much, then you've got a small enough moment that you've chosen. So again, think of a moment as being a small interval of values of the independent variable. However large the dependent variable values are, that's how large they are. But pick a small independent input sort of interval, and we'll go from there. So dx doesn't have to be like the size of this moment. Dx is the arrow moving, the thing that varies within the moment. So we're going to go back to our graph, and I've got an activity for you. We're going to do some computations, and I'll go through one with you. But if Julia and Derek, if you could pass out the worksheets, this is going to be something we're going to work on a little bit today. I'll give you some further instruction when you get them. And we're going to finish up talking about these in class start of Wednesday. But the idea is that within small moments, in this case of time, small moments, small intervals of the independent variable, we can talk about a rate of change at a moment if I can make that moment small enough so that I have an essentially constant calculation throughout that interval. So let me get back out of this, and I'm going to open up what you have. This is not the most recent one. Let's see. Moment. There we go. So it looks something like this. I think this is an old version of it, but We'll see. I think I updated this a little bit. But so what you see on here, it's just a chart. It's going to go along with our GC file that we had before, where we've got C, the current value of X in seconds, and there's a bunch of values labeled down the left side. Several at the beginning, because you know the beginning of the graph, it seemed to be more curved from a distance. The speed was changing more quickly, as we said. So what we're going to do is take a look at calculating what the M values come out to be, the speeds come out to be, at various starting values, various values of C in the graph, using different lengths of dx. Dx was the thing we could control with the slider. So just as an example, I think I started to do with a constant value of C equals 3, or current value, sorry, not constant value. Current value of X, C equals 3. Let me open this back up again and zoom out a bit. Oops. There we go. So, actually, let me set this back to regular. So, on this, again, if you have X going from like 0 to 10 or so, and Y from 0 to 110, you should, just doing that 2D graph range, you should be able to get back your whole graph and then zoom in on whatever portion you want. Now, what we wanted to do here was take a look at, I said, let's try C equals 3. So I played around with that a little bit with you, but I'm going to zoom in at 3 to be able to see what's happening instead of just seeing the computations up here. All you're going to be doing on the worksheet is filling in the results of computations, but it's more fun if you kind of see what's going on. And I want to point out that. So shift-click does a little box around. And I'm going to do it again because this is very small. Actually. So shift-click. There we go. All right, so around C equals 3, what I have on the screen here, it goes from, looks like 2.86 through 3.22. I could consider this whole, whatever I see in my screen, how far I'm zoomed in, maybe consider that whole thing to be our moment. And yours might be slightly different, but I've zoomed into a small section of this graph, which is, what, 0.4 seconds worth of it, where it looks like, to the naked eye, looks like a constant rate of change, looks like a straight line, not curved appreciably in either direction. So I can say, all right, this looks like a good moment. So again, my moment is this small interval of time over which it looks like there is, or it seems to be through computations, approximate constant rate of change. So what exact moment you pick doesn't have to be exactly 2.86 through 3.22, but I just wanted to point out that the moment isn't just where the arrow is on here. The moment is this whole section that I have decided is close enough, so let me do some computations there. So for the C equals 3 line, which is kind of in the middle of there, and you can get C equals 3, you can just change the value of C here. I want to look at the value of dx or look at the value of M when dx is 1, when it's 0.01, if I can get there, and when it's 0.001. Now, in terms of speed of doing this, it's probably faster to change the C value. I had it there. There we go. Change the C value and look at all the different values of dx. But picture-wise, when I've got dx's as 0.001, I can't really see what's going on here, but I can see that it says M is 10.7778. So in terms of your sheet that we're looking at, forgot to plug this in. Hold on. So in terms of this, I say, all right, when dx is 0.001 and C is 3, so that C is 3, 0.001, I've got in this spot here, 10.7778. So 10.7778. And then if I go back to that graph, let's see if I can do this. Which one am I looking for? This one. So if I go back to this graph and I change my dx value to 0.001, I can get there. Or 0.01, sorry. I'm going to get a different value of m, 10.7825, which what this means is that ratio of vertical to horizontal, 10.7825. Sorry, this is dizzying for me, so 10.7825. Or with dx is just 0.1. That one's the easiest one to get since that's the, just in the setup of the file, that's the maximum value of dx that we have. So dx is 0.1. We get m is 10.828. So 10.828. So depending on, within this moment that we chose, that goes from like, I don't know, 2.8 to 2.98 to 3.0 something, depending on what amount of time I go forward from 3, I do get slightly different values, but these are all very similar values of speed, how fast he's running. Now, what I will say about this, remember we talked about if we used all 9.58 seconds, that would just definitely be an average speed, because he clearly changed speeds over the time of that, meaning whatever speed we might have calculated, sometimes he was going slower, sometimes he was going faster. Now, looking at this, if I look at a whole tenth of a second, I calculate a speed as 10.8-ish, a little over. But if I look at a thousandth of a second, I get a number that's slightly lower. What does that say about his actual speed over the next tenth of a second? If the average speed over the tenth of a second is a bit different number than this, yeah. Yeah, he's accelerating. So if I use just the first thousandth of a second, I get a slightly lower number for his speed than if I go over a hundredth or a tenth of a second, which hundredths and tenths of a second are very small amounts of time. But I'm getting slightly larger computations, meaning during that moment that we saw, which was more than a tenth of a second long, it was like 4/10 of a second or so, he was actually accelerating. So if I want to talk about how fast he's going at time 3, this 10.8 something is more of an average speed because it uses a longer interval. The shorter value that I use, the more closely it links to how fast he's going at a point in time, although we can't just use a single point. So if I want to talk about his speed, though, the smaller this dx value is, the more accurately it represents how he's moving at the number that you assign to that at time 3. So in a moment at time 3, depending on how large a variation we let pass by in time, we get slightly different results. This one is the result that would be closer to what's happening nearer to time 3. If I go a little bit farther from time 3, it's not a lot far, but like a tenth of a second far, you can see he's faster. So that does mean he's speeding up, but I could use any of these numbers to do computations with. It just depends on what level of accuracy do I need. So what I'd like you to do between now and Wednesday is to complete this by doing, so for instance, just to show you what I mean, doing the other rows and then look at the questions about rate at the bottom. But so for instance, it starts with a value of C equals 0.25 seconds. So 0.25, put that in for C. You can get your values of M, but please look at the graph also and see what happens as you move to those different sections. You can just do the computations really quickly in this area on your GC file by changing and getting different values of dx and seeing what happens. And we're going to look at the patterns that you see on Wednesday, start of class. All right, so your assignment between now and Wednesday is mostly just finish this up. There isn't a Canvas quiz tonight. It's finish up this worksheet.